So the next conversation we're going to have is about something called a logarithm. And you really can't talk about exponentials without just going ahead and explaining what a logarithm is, because a logarithm is the inverse operation of an exponential function. So an example of that is like if I have x squared and I take the square root, that is the inverse operation. But the question is, how in the world would I get rid of it if I did this? What if I had a 2 here and an x up here? Taking the x root isn't a thing. Or better yet, it is a thing, but it has to do with this conversation, and it's called a logarithm. Because I mean, how in the world would you get rid of? You can't. You don't have an inverse right now. So the inverse is something called a logarithm. So a logarithm is the inverse operation of an exponential. It is the operation that cancels out this base. So what the logarithm will do is it'll allow you to be able to cancel this out and have this drop down. That'll come in a later section, but that's the idea here. So the way it works is logarithms were just basically created to do this. Take the output of an exponential function and make that become the input. Remember, the definition of an inverse is take your output and your input and reverse them. Your domain becomes your range, and your range becomes the domain. So the output is now the input, and the input is now the output, but the bases stay the same. You have to keep the bases the same in order for the inverse to work. So some students will say, well, why do I even need this? Like, why do I need a new function? So here's the basic idea that was thought up a long time ago by a mathematician named Napier. What happened is he was considering the idea that we know what 10 to the first is, right? 10 to the first is 10. And we know what 10 to the second is because that's 10 times 10, or 100. And of course, we know what 10 to the third is because that would be 1,000. But then the question now is like, what if I want to find what 10, what about 10 to something that comes out instead of 10? Of course, we also know what 10 to the 0 is because that's 1. So what if I wanted to know what I raise 10 to get 2, right? There has to be in between output values between 1, 10, 10, and 100, and so on. So he literally, many centuries ago, he literally made up these log books where he did these calculations by hand, and he started by saying, okay, well, I'm going to raise 10 to the 0.1. Okay, so that's 1.2589. And then he tried, well, how about 2? Okay, not quite to 2 yet. We're at 1.58. How about 3? Okay, we're awfully close. So now let's try 3.1. Okay, we went over. So now let's do 3.01. Not quite there yet. Let's put a 1 there. Okay, we're close, but not quite. 0. Getting closer. How about a 1? Not quite. How about another 1? Okay, very close, very close, very close. And as you can see, so then he backed up, and maybe it's a 2. Okay, maybe it's a 3, maybe it's a 4, maybe it's a 5, maybe it's a 6. It just kept getting closer and closer to 2, right? So then he would back up, and this took forever for him to do by hand. So look how close I got. I mean, with a computer and a calculator, I was able to figure out this exponent pretty quickly, but for him, it took months and years, okay? And it was so valuable. I'm just going to do a quick screenshot of this. It was so valuable that he wrote all these down, okay? And then what he did with them was he created a log of these solutions, and that's how they got their name. So again, I want to know what 10 raised to will become 1 or 2 or 3. And so you would look it up, and evidently 10 to the 0.30103 is very close to 2. And I think he took these out to like 5 or 6 decimal places. And so he wrote them down all down in a book, hence the name Logarithms, because it was like a log book of solutions. And they were published, and they were very valuable because there were no calculators at the time. So now that we understand that, he then created base books for everything. 10. You don't need a base book for 1 because 1 raised to any power is 1. But 2, 3, they all have their own, at the time, books. But he started with 10. So if you ever see log on a calculator or log on Desmos here, there's a log somewhere. If I just type log in, it is talking about log base 10. log base 2 or 3 would literally say a little 2 or 3 there. So let's take a look at how to rewrite equations in logarithmic form, because keep in mind that a logarithm is in fact an exponential written in a different format. So the way we do that, okay, is we simply take, right, we take the output and we make it the input, and we keep the base the same, and we take the input and make it the output. Start by just writing down that this is log base 3. So as a logarithm, this is the same base. So the output becomes the input, right? And then the input becomes the output. This literally is the exact same thing as this. So for instance, this one would be log base 1/2, same base. Input 4, it will output -2. This one would be log base 2, input 1/8, output -3. Okay, this one would be log base 49, input 7, output 1/2. And I'll explain what's going on with that one as I talk about all of these. And probably the most obvious one would be this one, because logarithms that were base 10 were just called log. So you don't write a log base 10, you just write a log. And basically the idea also here is that for a log base 10 system, then if you move the decimal place, I need one more 0 in there. If you move the decimal place over, it's equivalent to the value of log. So if I were to go into Desmos and type in log of 10,000, again, notice that it equals 4 because of the fact that logarithms of base 10 are really like doing scientific notation in science class. Now notice I can't type in log base 3. I can't even put a 3 in here. There is a way to do that, but it requires a theorem. So we'll talk about that at another time. So then we get to this weird e. Like, what is this e? E is a special number. I believe in it, even if you type it into Desmos, e. Look, it has a value. It's like pi. And this is what's known as the natural constant, or the it's a growth rate that appears in nature. It first was discovered in financial calculations, actually, but it tends to relate all of the logarithms together, especially when working in real life problems. So e is equal to 2.718. It is like pi. Pi is 3.1415. E is 2.71828. It's more important than pi, actually, because pi only relates the circumference of a circle to its radius, and e relates all logarithms to each other, potentially, in certain calculations, as well as gives human beings a way to relate all exponential growths and decays in the natural world. So it's super important. In fact, it's so important, like this problem, if I were just trying to use the knowledge, right? This is the base. The output becomes the input, okay? And then that will equal the input. This is so important that this thing, actually, you can see I accidentally wrote it down wrong. This gets its own special name. So log base e is called the natural log. So again, we would have started, had we not known, there's no such thing as, this is the only special logarithm. So log base e is actually called natural log, and that is something you can type into a calculator. It is instrumentally important. As an Algebra 2 student, you just need to realize that there's a special logarithm. Here, I'll show you. You can type ln in. So if I were to type ln into the calculator and type in 7.38905, you can see that it's very close to 2 because I need another decimal place. But ln is something you can type in, and log is something you can type in, but you just need to understand the difference between the two. So how does this work? This is how I always check my work. I go like this. 3 to the second power should equal 9, which is what I started with here. 1/2 to the -2. Remember that negatives reciprocate fractions. Then squared would be 4. 2 to the negative 3 would reciprocate, and then raising it to the third would be 8, so 1/8. 49 to the 1/2, remember 1/2 is a square root, so the square root of 49 is 7. And then here, remember we would have a 10, right? So 10 to the 4th is 10,000. And then e to the second power is this. So maybe check it like that. It's very helpful to check things in that manner. And that's actually how we do the next problems. So the next problems are, you have logarithms, write them as exponents. So if you check your logarithms the way I'm showing you, this is sort of, it's just super easy, right? So 6 squared is 36. Some people like to start with these problems on the homework before they do these. But obviously, I needed to show you exponents before logarithms because we know about exponents. But defining a logarithm as an exponent sure does make logarithms make more sense, right? So this one, notice I wrote it in a different order. Remember, there's a 10 here, so 10, right? As long as you keep the flow in the right direction, you won't have any trouble. Keep in mind, this would be e, so e to the 1/2 will be this. So it's really not that hard. Maybe when you try your homework, try with the logarithms and write them as exponents. Some people just skip over exponents when they talk about logarithms, and they just start talking about logarithms. And I find that to be a little bit confusing. So I showed you the exponents first, and then I'm asking you to do logarithms, but maybe you start with the logarithms to see how they work, and then redefine the exponents in that way. So hopefully, as I was talking, I was writing, hopefully all of these make sense, okay? And the thing I always ask students is there anything, that doesn't have the right flow? I mean, basically, is this true? Is 6 squared 36? Yes. Is 5 to the negative 2, remember, reciprocate the 5 to a fraction and then square it, so yeah, 1/25. This is just scientific notation. Move the decimal place from here, from here, 3 to the left, so that works. 2, reciprocate it and raise to the 5th would be this, and then here we get this weird thing we've never seen before. And I will remind you that 1/2 also means square root, so it's probably better to even write that like that. And if you go to Desmos and double check that one, I advise that with all of the ln's and e's that you have to do, it would work out. So you could either type in the square root of e, or you could type e to the 1/2. This is the better answer, believe it or not, is to realize that it's actually 1/2 is a square root. So the last thing here is evaluating logarithms as a number. Now, why does this matter? Imagine you have an equation, right? And you have like x plus log to the log base 5 of 125, and then that has to equal 7. Well, this is actually an integer. How is that possible? And that sure would make it easier to solve. Because if we understand how this works, right, we can understand how this works. This is saying 5, we don't have the answer over here, so 5 to what power is 125? Well, the answer to this is 3, right? 5 to the 3rd power. So if I were trying to solve this equation, this would just be 5 plus 3 equals 7, so x equals 4. So you can see why it's important to be able to evaluate a logarithm expression to an actual integer value. So for instance, in this one, log of 100,000, what does that equal? Well, it's base 10. So 10 to what power is equal to 100,000, right? That is just scientific notation. Again, all I'm doing is that same flow. 10 to this is equal to this. And this one, again, 5 to a question mark is equal to 125. So just count the zeros, 1, 2, 3, 4, 5. So this answer would be 5, right? This one would be 2 to the question mark. I don't know what the exponent is. That'll give me this value. Again, it's asking you what this is, right? So 2 to this is equal to that. So we know the answer has to be negative because it reciprocates. Remember, this can never be negative, but an x component can be negative in order to create a reciprocation. So the question is 2 to what power is really equal to 16? So it's going to be negative 4, right? 2 to the negative 4 is 1/16. 2 times 2 times 2 is 16. Negative reciprocates. And then we get this amazing question. What in the world is it asking? Remember, the base of this is e. So e to what power is equal to e? So e to what exponent equals e? And the answer to this is 1, right? Anything to 1 is itself. Here's a sister question to this question is what if I said anything, what if I said ln of 0, right? So the question there is e to what power would become 0? And that has no solution, right? E cannot be raised to a power to get 0. That's impossible. That's important to understand, okay? So you can make something become itself. You cannot make something become 0.